Hello everybody, thank you for attending this talk that presents an integrated multi-objectives, sensory and robots task space control using quadratic programming. Nowadays, robotic trends can be illustrated through these 5 pictograms. Robots can operate in unstructured environment, even in SME and mini factories, and hence must deal with uncertainties. Robots are also used in services and might require high cognitive interactivity, namely when the service concerns human-robot partnership of various kinds. Robots share the same space with humans in mini factories but also in domotics, and hence must be intrinsically safe in human close contact interactions. Robots have several sensors and can be reconfigurable or can work in complement to other robotic systems. And finally, robots need to be embedded with learning capabilities to ease their programming. For many years, programming a robot consisted in defining the robot model, that of the environment, and the goals to be achieved. Then, we need to plan successively tasks, path for each task and trajectory for each path. The control consisting mainly in tracking the trajectories. Despite its success, there are several limitations to such an approach, such as its computational costs and scaling to complex systems and environment. The a la mode trend inherent to the revival of AI is to replace all the previous steps by a deep learning network connecting the goals directly to the joint space of the robot. We have rather adopted the task space approach for its elegance and its capability to deal with complex systems by controlling the robots directly in the task space. It means without generating explicitly trajectories. Task space control can also play the intermediary buffer between the low-level joints and the intelligence. Let's have a quick tour into the fundamental aspects. In a multitask control formulation, we can define as many tasks tau k as one wants the robot to achieve. A task being any feature we want to control on the robot. Each task would then require a finite set of robot resources that are the sensors and the joints, which availability could eventually not be fulfilled for each task. In this later case, the tasks are said to be conflicting. A compromise is then needed that is usually resolved through prioritizing the tasks in a strict, soft, or a hybrid fashion. The control formulation is a particular instance of the following general optimization problem. There is no perfect solution to this problem. The ideal point is not a solution in general. There is a whole set of optimal solutions that have different names. Pareto optimal, efficient solutions, non-dominant point, etc. Soft prioritizing tasks is defined as solving the following weighted sum scalarization minimization problem. Whereas strict prioritizing tasks is defined as solving lexicographic scalarization minimization problem. In order to have further theoretical insights, please refer to our TAC paper addressing these issues. We conceive task space controllers by defining the task function f for a given sensory error e that can be a cost to achieve at best, or inequalities or equalities to meet strictly. Then we build complex controllers as a computer program, that is to say, from simple basic controllers templates that form instructions and a finite state machine for branching. According to our view, each task is a motion primitive under constraint. Let's define few templates. The setPoint task. The setPoint task is defined as an error E, function fp of the robot configuration state Q. The robot feature to control is a frame attached to its gripper. The goal is to reach the green ball. We also define the AR first and second derivative that pop up the robot Jacobian and its derivative respectively, and the robot configuration and its velocity q dot, and the acceleration q double dot. Another task could be to reproduce the green ball trajectory. This is defined as a tracking problem, which will require first and second derivative of the ball's trajectory. The visual servoing task is defined similarly to the setpoint task, yet using the visual servoing Jacobian LV to connect the image space with the robot joint space. In Aggravante et al., published in RAL 2017, the interaction matrix is computed in the error acceleration space. Here is a video showing a visual servoing reaching task, including whole body walking tasks and other tasks that we do not describe. Let's end with a force task template example. In this case, the task is defined directly in a function ff of the force one wants the robot to apply. In practice, the implementation on high gain position-controlled robots is made through admittance. The particularity of the task-based force control formalism has been thoroughly discussed in Boyerman et al., published in TRO in 2019. Now, we have in hand a set of usual task templates that we can use to achieve a multi-objective goal or mission. Of course, we can create new ones or compose new templates from the predefined existing ones. For the robot to achieve the goal, we assemble all tasks and their constraints into a QP optimization problem. The decision variables of the QP controller are the joint acceleration, external, example contact forces, and torques. Now we have a multi-modal QP that integrates setpoint, vision, and force tasks in demand in a single formulation with task-specific constraints, which can be setpoint, vision, or force-based constraints. Dynamics constraints linking forces, torques, and joint acceleration through a locally affine equation, fixed contact, friction cone, torque and joint limits, and collision avoidance constraints, etc. For example, in a recent demonstrator of a humanoid robot operating in a real aircraft manufacturing setting of Airbus at Saint-Nazaire, we achieved the predefined goals using this type of controller. Notice that visual servoing, which also requires keeping both the objects of interest and the gripper in the robot embedded camera field of view, a setpoint task to reach the target where the object is to be assembled, and force task to assemble that object, all under balance constraints implying the center of mass, collision avoidance, torque limits, etc., are solved at each QP iteration of the controller. You can find a video concerning this demonstrator attached to the paper published recently at IEEE RAM 2019. We could also extend the controller to include objects the robot interacts with as additional passive robots or even other robots that are somewhat added into a gold controller that keeps the coherency of the interaction forces. In this example, the drawer, for instance, can be seen as an additional robot with whom the humanoid robot interacts. How do we do feedback then? Well, the inertia could be online estimated, and the state could be also online estimated using pose and joint estimation with the robot embedded camera. Moreover, one can even add low-level controller gains, the PD gains in this example, as part of the QP decision variables. We used it to tune the stiffness damping of the actuator to reflect different impedances. How? Notice that the torque can be replaced by its explicit controller, which gains are affine with respect to the dynamic equation. Theoretical and technical developments of the previously described controller are gathered into a framework we named MC-RTC. This framework integrates all the necessary components and computations to automatically build the QP control problem from task specification, robots URDF models, etc. The controller is then made to be interchangeably connected with the robots to be controlled or existing simulators such as humanoid, VRAP, and recently AGX from Algorix. It may or not use ROS and OpenRTM depending on the user's choice. We also use RVs for interactive concurrent visualization of the controlled robot and the simulated one, or the real one, and stored data for debugging purpose. In order to get started with the framework, you could install the framework directly from the website, install the interface of your choice, write a controller for your robot, and run the interface. In this slide, we show how we go on to write a very basic controller for any robot. Well, first, get a robot, either a complete robot module or simply your RDF file. See later Anastasia Spolotnikova's talk in this workshop where she will introduce a complete MC-RTC robot integration. Then create a controller template and build the empty template. Configure MC-RTC to run it. For instance, let's assume the main robot as the default Panda and enable the Panda sample controller already available for everyone interested. Et voila! Running the controller gets you a poster task that you can play around with. You can also insert an arbitrary end effector task. Later in the video, the poster task is removed to show the interaction between the tasks. What the video does not show is the controller respects all the robot limits, joint torque, position, velocity, and that the controller avoids self-collision, result of minimum extra work to specify the collision set. Let's have a peek at the controller code that just ran. Very simple stuff, is beautiful. What you have is the MC-RTC, the reset, and then all the constraints that are added, like contact constraints, dynamic constraints, set collision constraints, set the poster task, and then run. We will see now how we structure complex controllers. We are using for that purpose state charts. State charts are composed of two main elements, states and transition between those states. State can be a state chart, multiple states can run in parallel, and in MC-RTC, a state is a class with three methods. Start, that is called once when the state starts. Run, which is called every iteration while the state runs. Tear down is called once when the state stops. States are easily composable and highly recomposable. We show it here in practice with a controller that can let a humanoid open a door. Initial step almost identical to the regular controller. Extra configuration to the controller is load extra robots, shown here, and note that yes, the door is a robot. Specify the constraints active on both robots. Specify extra collisions. Specify the initial set of contacts. This is the overview of the open door demo. Initial creates a button to start the demo. Open door demo is a parallel state. Standing keeps the COM in its initial position and chest orientation. The open door FSM is a nested FSM. All states except initial are going to be implemented in a descriptive way. No code, just YAML. This slide shows the C++ code for the initial state, mainly to show the logic of a simple state and the ability to add elements to the graphical user interface in a very straightforward way. This slide illustrates how an internal FSM is specified. The same is applied for the global one, but it's much simpler. We have the specification of the base, whether we go step by step, and the transitions. Now, we show how we can create new states out of an existing one. Rotate handle is based on a C++ state used to target a specific posture which prescribes a configuration format. Open door and rotate handle back just change the target of the rotate handle state. Note that the door motion is only prescribed by door commands. The contact between the robot's hands and the door handle will give agency to the door. A few more YAML states and the video shows what can be achieved with a very simple FSM controller, less than 100 lines of codes and configuration, and very few code. In reality, door position can be provided by a vision algorithm. Force control can be applied to reach the handle safely. Better, vision force control can be applied to reach the handle safely. It's not hard to do in MC-RTC, but little too much for this time. What's coming next? MC-RTC currently makes it easy to write a program from existing bricks, yet TVM will help creating new bricks. FSM, graphical edition, makes it easier to navigate and understand complex controllers. Let's conclude our talk. MC-RTC is a powerful task-based control framework that achieves multi-objective sensory and robots' complex behaviors. It's open source and flexible for all kinds of users, students, researchers, and robotic providers. It has already steered several robots, among which humanoids. See the presentation of Anastasia Bolotnikova in this workshop for using MC-RTC to steer SoftBank Robotics Now and Paper in a human-robot physical interaction applications. Future work is still ongoing to deal with robustness and automated coding to reach a code-free controller. Thank you for listening.